Okay, welcome. This is going to be lesson 1.5, which is all about inverse functions. So this unit so far we've touched on the definition of a function, the domain and range of a function, which is like what can you plug in, what can you get out. We've talked about graphing functions and interpreting domain and range graphically. And then we did transformations on functions and function compositions. So the next bit is how do you undo functions? So you can think of a function as a machine taking inputs and sending them to outputs. Could you determine a machine that does the reverse of the function that you're interested in? And that's what inverse functions are all about. It's how you take your output, your answer, and work backwards to find what the original input would have been. Okay, but first, we have to talk about what one-to-one functions are. So here's our definition for one-to-one. A function f is called one-to-one if for every y that's in the range, there's exactly one x in the domain where f of x gets you y. So it's kind of like the definition of what a function is, where the definition of a function is every x goes to exactly one y and not more than one. This is saying every y, there is one x that went to y when you applied the function to it. So it's like kind of saying that if you were to go reverse, then that's going to be a function. So here's some examples of one-to-one functions. 2x plus 1, a linear equation, is a function. The square root of x is a one-to-one function. 2 to the x is a one-to-one function. So these are all examples of one-to-one functions. It's a lot harder to prove that a function is one-to-one than it is to prove that it's not one-to-one. Because to show that it's not one-to-one, all you have to do is find one y in the range that has two x's that go to that same location. Okay, so let's look at a couple of non-one-to-one functions, and I can find you, we're going to find a y where there's two different x's that go to that same y. So for example, x squared. That's not a one-to-one function because let's look at the y 4. So if y is 4, then x squared equals 4 has two different answers, or two different, there's two different x's that are going to get you 4 as the answer, right? So we have -2 and 2 are both going to give you 4 as the answer under x squared. So it's not one-to-one because we found a y in the range where two different x's map to that. And this is saying we need exactly one and not two, okay? So again, graphically, or with like domain and range blobs, you can kind of think of it this way. This is the range, and this is the domain. And we found 4, and we found two different x's, -2 and 2. Both of those map to 4. With our square root or squaring function, and so that's not going to work. It's not one-to-one, meaning there's no like we found a y where two different x's went to that. Okay, absolute value of x, also not one-to-one. So absolute value of x doesn't work because, for example, if y is 5, well then absolute value of x equals 5. You can think of two different x's where you take the absolute value and you get 5. So for example, -5 and 5 are both going to get you 5 as the answer. And so to be one-to-one, you can't have two different things going to the same output. Okay? X cubed minus x, also not one-to-one. This one's a little trickier to think of. Answers that are going to have more than one input going to that. But I could tell you that the answer 0, so if y is equal to 0 for this one, y equals 0 has multiple answers, multiple x's that are going to get you that. For example, 0, so x equals 0 would be an answer because 0 cubed minus 0 equals to 0. And x equals 1 would also be an input that goes to 0 because 1 cubed minus 1 is equal to 0, right? And so in this case, now we've got 0 and 1 are both going to the answer 0, and that's not allowed for it to be 1-to-1. This is x cubed minus x. The other one was absolute value x. Absolute value x. So to show something's not 1-to-1 is relatively simple. You just have to sit and think, okay, let me find a y where 2 x's go to that answer. Absolute value was pretty trivial. X squared wasn't too bad. X cubed minus x took a little bit more thinking, but we found 2 different x's that go to the same y. Okay, so there's another approach to thinking about one-to-oneness, and that's the graphical approach. And the way to determine if a function's one-to-one graphically, it's called the horizontal line test. It's similar to the vertical line test, except vertical line test tells you if it's a function or not. The horizontal line test tells you if it's a one-to-one function, okay? So in order for it to be a one-to-one function, it's got to pass both vertical line test and horizontal line test. And so a horizontal line test says that a function is one-to-one if every horizontal line intersects it at most one time. So you can see this function on the left, x cubed, it passes the horizontal line test because if you were to kind of draw horizontal lines on this, continue to draw horizontal lines, none of them are going to hit it more than once. It looks like maybe it hits it more than once at 0, but it actually just hits it exactly once at 0. And so what this is saying is the same thing, is that every y has at most x, at most one x associated with it. And if you look over here on the right, you can see that this absolute value function fails the horizontal line test right here. I mean, it fails it in a lot of places. But for example, if you draw this horizontal line, you see it hits twice, and we drew the line y equals 2. There's our y value, where we have 2 different x's that go to the same answer. What are those x's? Well, the x's are 2 and -2. The x coordinates of the intersections, right? So you drew your horizontal line at some y value, it hit it twice, and the x coordinates are those x's that would give you that y value. So not one-to-one. So this is not one-to-one, and this one is one-to-one. Okay. So that's the horizontal line test, and that's that tells you if functions are one-to-one. Okay, so you can actually make a non-one-to-one function into a one-to-one function by specifying or restricting the domain down so that it does in fact pass the horizontal line test. So here's 2 examples. We've got x squared over here. We have the graph of x squared, which we already know is not one-to-one, and you can tell it's not because this horizontal line hits it twice. In fact, lots of these horizontal lines hit it twice, right? So that's not one-to-one. And if we did x squared with a domain from 0 to infinity, we would end up getting a one-to-one function as a result of that. So this is the same rule, x squared. Take your input and you square it, but you're actually just saying, I only want to be able to apply the function to numbers that are 0 and more. So your domain is 0 to infinity. It is restricted from x squared's domain typically, which is all real numbers. And so when we restrict the domain down now in this way, you can see that it is one-to-one, because if you draw horizontal lines, you only hit it once now. And so this is an example where we took a function that's not one-to-one originally, and then we just took a piece of it, and it became one-to-one as a result. Okay? So this will be something that you might have to do in order to, in the next step, be able to find an inverse for a function. Is you'll have to take a chunk to make it one-to-one in order to be able to figure out what the inverse is. Okay, so this leads us into what the inverse function is. So here's a definition for the inverse function. So starting with a one-to-one function, we need it to be one-to-one first in order to find the inverse. We're going to call f inverse, this is f to the -1 power. Now, it's not to be confused with raising it to the -1, which is actually doing 1 over that number. For example, 2 to the -1 is equal to 1/2 because it's 1 over 2 to the 1. F to the -1, we're actually calling the inverse function, or the inverse of f. And so these two are not the same. It's not the same. It's a little confusing notation. But we use -1 power as the undoing. It's really not -1. It's not a power. It's just saying the inverse of f. So with that aside, we call f to the -1, but it's not to the -1. It's just written that way. The inverse of f, where for each y in the range of f, f inverse of y, or the inverse function on y, gives you x, the x where f of x equals y. Blah. All right, let's try to say that one more time again. So starting with the one-to-one function f, we're going to call f inverse, the inverse of f, where each y in the range of f, you apply the inverse function on y, and that's going to give you the x value, where if you plugged x into f, you get y. So this is the undoing function. If f is the thing that takes you from your inputs to your outputs, f inverse takes you from an output to the input that you would need to plug into f to get that output. Okay? So you can think of it like, again, doing the machine in reverse. So if the function f takes this x and sends it to that y, so that's f in action, then the inverse function takes this y and sends it back to x where it came from. Okay? That is the inverse function's job. It is to undo what f did and give you what you started with. So a couple things to note about functions and their inverses. F has to be one-to-one in order for there to be an inverse function. So occasionally what that means is you'll have to specify what the domain is for f in order to actually make it a one-to-one function so that you can find its inverse. A lot of functions are one-to-one and can be inverted right away, but some of them you do have to make smaller and not take their entire domain to make it an invertible function. The domain of f inverse, which are where the numbers that you plug into the inverse machine, well, those are coming from the range of f. And then the range of f inverse, which is the answers of f inverse, they're going to give you the x's that started in the domain of f. So the range of f inverse is the domain of f. So the domain of f inverse and the range of f inverse are the swap of the domain and range of f. So you can kind of see that on the picture over here on the right. You can see that if your original function's domain is x, then that becomes the range of the inverse function. And your original, I used red, let me use blue because it's all blue. Your original range of the function is y, that becomes the domain of the inverse function because the inverse function's job is to take an answer and give you back the original value, the original x. Okay, so these guys swap for the inverse function. And then this is a very important property of the inverse function, is that the inverse composed with the original function gets you what you start with in either case. So if you do inverse of y and then you do f on that, it's going to give you y. And you can think of it like this. So the first one is saying, find me the x where f of x equals y. So f of f inverse y is going to equal, well, the inside part is equal to the x where f of x equals y. So this right here, this part in the middle, is equal to some x value where you take f of that and you get y. So if you take f of x, what do you get? Well, you get y, which is what you started with. And then this other one is saying if you first apply f to something and then you take the inverse of that, then again you get what you started with. And the reasoning behind this is f inverse of f of x, right? So what is this equal to? Well, f of x is equal to some y, and the f inverse of y is equal to x where f of x equals y. And so this thing right here is the same y as that thing over there. Okay? And so inverse function composed with the original function ends up giving you what you start with in either case. And the way to think about what the inverse function is it's the undoing function. So I give you this little cute drawing I found on the internet where the function f is responsible for turning apples into lemons. So your apples go into the f machine. Those are your inputs. So these are your x's. And then they come out as lemons, because why not? Apples can turn into lemons. And the inverse function's job is to turn lemons back into apples. So if you do this chain, where you do f of x and then you do f inverse of that, you get what you started with. So this is a picture for, this would be f inverse of f of x. Because you're plugging an x into the f function, you're taking the answer to that, plugging it into the inverse function, and then you're coming back out with, up with what you started with, which were apples in this case. Okay? All right. Let's get some concrete examples going on, and how do you actually compute these inverse functions. But this is the high-level stuff, what you need to know about them. Remember, the domain and range swap when you're looking at the inverse. The function itself has to be one-to-one to have an inverse. And then when you compose a function and its inverse, you get what you start with, which is either x or y, depending on if you're doing f of f inverse or f inverse of f. Okay. All right, so to determine the inverse of a function algebraically, it's really just a set of solving steps. You're going to replace f of x with y and then solve that for x. So here's an example. So suppose our function f of x is 3x minus 4, and we want to figure out what is the inverse function for this linear function 3x minus 4. So here's our first, our step is we're going to replace f of x with y. And so now f of x, which was here, is now equal to y. So we say y equals 3x minus 4. And then we start solving for x. So we solve for x here. Okay, and this just takes some algebra steps to do that. So I'm going to add 4 to both sides. So if we add 4, then we're going to get y plus 4 equals 3x. And then we're probably going to divide both sides by 3. Divide by 3. And then we get y plus 4 over 3 is equal to x. So x has been solved for. And so now we've got our inverse function. F inverse of y equals y plus 4 divided by 3. And so it's just the f function, but in reverse. So let's test out our hypothesis that f of f inverse of y is equal to y. So let's go ahead and plug f inverse of y into the original function, see if we get what we start with in this case. So f inverse of y is y plus 4 divided by 3, so that's going to go in here. And so this is going to look like f of y plus 4 divided by 3. And so how do we figure what this is? Well, we see that f multiplies inputs by 3 and then takes away 4. So we're going to substitute this guy, here let me use another color, this guy here right into that x, because we're doing the f function now. So we're going to have 3 times y plus 4 over 3 minus 4. And now we just keep solving. The times 3 and the divide by 3 cancel. We get y plus 4 minus 4. Plus 4 minus 4 cancel, and that just ends up giving us y. And so we got what we started with in this case, which was y. So you could also do the opposite, f inverse of f, and see that you get x, what you start with, and you should. So this is our inverse function for f of x. Okay, let's do a couple more examples. So suppose our function is x minus 1 squared plus 1, and we want to ask the question, what domain would make f 1 to 1? Because I can tell you that it's a parabola, and if you think about what the shape of a parabola looks like, it's a U, and it doesn't pass the horizontal line test because there's going to be 2 different x's for certain y's, right? So let's go ahead and take a look at the graph. And if we look at the graph, oops, there we go. If we look at the graph for x minus 1 squared plus 1, we can see, yes, it does in fact fail the horizontal line test. So we're going to have to decide how much of this graph we can take. If we start it here at 1, we can go from 1 to the right, or we can go from 1 to the left. And that's kind of our only 2 options, two good options for domains for the inverse function. So let's look at, if we were to take everything to the left, that means we want 1 and less. And if we were to take everything to the right, then we'd want 1 and more. And so either of those domains are going to give us a nice 1-to-1 function. Okay, so either from negative infinity to 1 or 1 to infinity would be our domains, so that it is a 1-to-1 function. Alright, so now what's the inverse function for f? Now that we've decided, well, depending on which of these domains we choose, this one or this one, we're going to end up with actually slightly different formulas for the inverses. We'll see in a moment. But let's go ahead and try our steps of solving for x, plugging in y and then solving for x. So let's see, what would we do to undo things here? Well, I think I'm going to take away 1, so that's going to give us y minus 1 equals x minus 1 quantity squared. Now I'm going to take the square root, and see, now we can see why we're having problems finding the inverse function. When we take the square root, we get both plus and minus signs coming out of this thing. So we have the square root of y minus 1 equals x minus 1, and then our last step would be to add 1 to both sides. And so that gives us a formula, the square root of y minus 1 plus 1 equal to x. And we have this funky plus or minus thing we have to deal with. So what this plus or minus thing is telling us is that the function is originally not a 1-to-1 function. And so if we choose the red domain, the left one, negative infinity to 1, then what we're effectively saying is we want the negative square root. So we'd want this negative square root right here. So that is going to be the inverse function for x minus 1 squared plus 1 with the domain negative infinity to 1. And you should think about why the negative square root is what we want for this. That's because these are all, for the most part, negative numbers, and this is the domain of f. And the range of this function, so if you look at the range of this, its range needs to be the same. So this range needs to be the same as f's domain. And we have minus a square root of something plus 1. You can see that this range matches up with this domain exactly. Okay? So remember, the domain and range, the domain of the original function is the range of the inverse function. And then if we were to do the other domain, we would be using the positive square root. I'm going to put myself back up there. So the positive square root is going to get us the other domain. The other domain is going to get us this positive square root out. And you can see that this domain, again, 1 to infinity, matches with this range. So the range, again, matches to the domain that we chose. Okay? So this is a weird function. It's hard. It's a little tricky to think about, but just remember, if it isn't one-to-one, you're going to end up having to make some choices here about which part of the function you want. And once you made that choice, then it might pop up in the formula that you come up with it might come up in the formula for the inverse function. And it did in this case, right? When we took the square root, we had both plus and minus answers, and we got the plus answer when we took one domain, and we got the negative answer when we took another domain. Okay? Okay, let's look at another example that's a little bit more algebra heavy. So we're going to have a rational function here, x plus 2 over x minus 1, which again is a function that just says add 2 to x, take away 1 from x, and then divide those two results, and that's your answer. Let's look at what domain would make this function one-to-one. So we'll graph it, and we can observe from the graph if it passes the horizontal line test or not. And here's x plus 2 over x minus 1. We can kind of see that, yeah, it does in fact pass the horizontal line test. We don't have any weird blips where it kind of like U's out somewhere. And we've got this weird bit where it's never hits 1 as our y value, but there's no overlap, right? There's no everything over here on this curve is less than 1. Has a y value less than 1, and everything on this curve has a y value more than 1, and so there's zero overlap. Our domain, if we looked back at the original function, we can see that the domain is everything but 1. So that's going to be our domain we take for the inverse function, because that's the domain of the function f. Okay, so we're going to get the whole thing when the whole thing it's already one-to-one. Alright, so what is the inverse function for f? Well, we're going to set y equal to x plus 2 over x minus 1. And now we have to solve this for x. And we see x shows up in 2 places, so it'll be a little tricky. It will require some algebra to solve for x. Now what I would do when I'm facing this problem is I'm just going to start trying stuff rather than just giving up. And so one thing you might try is to multiply both sides by x minus 1. So let's try that and see if that gets us closer. So that will get rid of our denominator on the right and put x minus 1 onto the left side with the y. Okay, so now we have y times x minus 1 equal to x plus 2. Again, our goal is to get x by itself. So now, I can't, if I divide by x minus 1, I just go back to where I started. So let's go ahead and distribute that y through. So we get yx minus y. And yx minus y equals x plus 2 now from that step. So I've got some x's here on the left and some x's on the right. Let's try to collect those x's because that's what we're doing when we're solving. So I'm going to move this this yx over to the right hand side. So we'll take away yx from both sides, and that cancels with it on the left, and we're getting closer to x all being together. And then the next step is I'm going to take away 2 from both sides. So there's -2 and -2. And so that gives us a side, the right-hand side now has only x in it. Excuse me. And we're closer to having x being solved for. We have -y minus 2 on the left and x minus yx on the right. Now you can note that an x is common, right? There's an x here and an x there. And so when you have a common factor, you can factor it out, just like we did there. So when we factor x out, that leaves us with 1 minus y. And just to remind you that x times 1 minus y is in fact x minus yx, we can just distribute it back in, see that that's what we started with. X minus yx is equal to x times 1 minus y. So now we have x by itself. Basically, the last one little step is to divide both sides by 1 minus y. So when we do that last step, we now have x by itself. And we could do one last little cleanup step here, which is we've got lots of negative signs, and I don't know about you, but I'd rather remove as many negative signs as possible. So that last final little step you might do is to multiply the top and bottom of the left-hand side by -1. So this isn't going to change anything. It's just going to get rid of a bunch of negative signs and ultimately give us this equation for x, which is y plus 2 over y minus 1. Because when you multiply 1 minus y, when you multiply this by -1, you end up getting -1 plus y, which you can reorder as y minus 1. So there's our final answer for the inverse function. F inverse of y is y plus 2 over y minus 1. So it turns out the inverse function is the original function as well. So you plug in a x, you add 2 to it, you divide it by that value minus 1, and if you were to run that machine backwards, you do the exact same thing, and that would give you your inverse function. Okay, last example. Show that if mx, or if f of x is equal to a linear function mx plus b, then the inverse function of y, or the inverse function is 1 over m times y minus b over m. Okay, so we know that the function composed with its inverse gets you what you started with, so we're going to compute this composition and see that that holds, because if it is true, then that is the inverse function. So if we do f inverse of f of x, then we're going to do f inverse of mx plus b. So here's my function f of x equal to mx plus b. So I'm going to replace f of x with what it is equal to, mx plus b. Now the inverse function says replace all occurrences of y. So anything that's got a y in it, we're going to replace it with what we put right there. So now we have f inverse of f of x is equal to 1 over m. That's the 1 over m. We're replacing y with mx plus b. So there's our mx plus b right here. And then we're going to multiply that by 1 over m and then take away b over m from that. So let's simplify this, and hopefully this should equal x at the end of the day. So multiplying through the 1 over m is going to cancel with the m multiplying x and put a factor of m below that b. So we end up getting, after distributing, so after this distributing step, boom, boom, we're going to get x plus b over m. And then we have a minus b over m, and so boom, those guys cancel, and that gets us x. And so because we get x after composing these, we know that it's the inverse function. These two functions are inverses of each other. We could also check f of f inverse equals of y equals y, and I would encourage you to do this as an exercise, but you should get y, and it's sufficient to just check one direction of the composition and not both to see if it's an inverse function or not. But as an exercise, I would say go for it and do that as practice. Okay, that's the end of this video, and we'll get a bunch of practice doing inverse functions on Monday. So hopefully you have a good weekend, and I'll see you then.